Okay students, so welcome back to our YouTube channel School for All. So today we are doing further complex number part 2. Yeah, so we see answer a sample GCE question. So I would first of all like to do a record here on similarity transformation, or similitude transformation is the same thing. So before answering our sample GCE question today, we first of all do a small recall on similarity transformation. Now, what is the similarity transformation? The small definition of a similarity transformation. So definition: similarity transformation, which is also called a similitude, is a transformation that preserves, it preserves the shape, but not necessarily the size of the object. Yeah, that is the meaning of similarity transformation. It's transforming an object to an image by preserving the shapes, but not necessarily the size, because it sometimes changes the size by maybe you can enlarge or reduce the size of the object. Okay, now it means that any complex number written in the form so that is any complex number written in the form z equals to a z and z prime equals to az plus b. Exactly. Any complex number written in this form where a is different from 0 is okay. Any complex number written in this form, the transformation that is described by this equation, let's say maybe that transformation t, forms what? A similarity transformation of radius a. So forms a similarity or a similitude similarity transformation of radius a. So that is it. So that is what you should know. Any complex number written in this form forms what? A similarity transformation of radius a. Now let us go to types of similarity transformation, or we talk also about geometrical interpretation of the transformation. Now here to study let's say the transformation of a plane, or to study the transformation of a plane, to study the transformation maybe of t. So to study the transformation of t, the first thing to do here is to first of all write the complex number in the form z prime equals to az plus b, where a and b is what? A and b belongs to a couple of complex number. So that is it. You first of all write a complex number in this form. So any complex number written in this form already forms what? A similarity transformation. Now, for us to come out with the geometrical interpretation, let's say types of similarity transformation, what are we supposed to do here? The first condition is to see. Now, as I was saying, the first condition is to see the value of a. If a here equals to 1, if the coefficient that is multiplying our object is 1, it means that t here is translation. So it means that the transformation is only what? A translation. It means that t is translation. This is translation of complex vector. Translation of vector b means I'm only translating. It's okay. I'm taking z, I'm translating by b. So if I want to see it algebraically, it's simple. If I have my let's say real axis here and my imaginary axis here, it's okay. So if I want to translate, let's say m, let's say point maybe m here, is the object. Therefore, if I want to translate by the vector b, I will come, look at this, a straight line. I will translate it like this is m prime. I'm just translating by what? By vector b. So that is the meaning of translation. Okay, so the next condition, you see that if a now equals to -1, so if the coefficient of z multiplying the object is -1, you see that what? You see that t now will be a what? T now will be a symmetry. Is okay? T now will be a symmetry of center b all over a. So t here will be what? T T, the transformation is a symmetry of center B all over A, as easy as that. So anytime you're having a complex number written in the form Z equals to negative Z plus another one, which is B, or B can also be complex number, it can also be 2, it can also be 2 plus I. Anything, you know that what, since the coefficient of Z is -1, it means that T is a symmetry of center B all over A. It means that to find the center, you take B, you divide by A. It's okay? Then let us see the next condition. The next condition is that if A belongs to a set of real numbers, means that if A is real, excluding -1, 0, and 1. So this means that A can take the value half, A can take the value 2, can take the value 3, can take the value 4, can take 1/3. It's okay. You see that here now, A is not 1, A is not 0, A is not -1. It means that A already is what we call scale factor. Is multiplying, is rather increasing our Z or reducing. It's okay. It means that here T now will describe what? T will be simply describing what? T will simply describe what we call homotheity or a scaling. So T is a scaling. In bracket, it means an enlargement or a reduction. It depends. As I was saying, if maybe A is 2, we are enlarging, because if A is 2, we are multiplying by 2 and enlarging. Reduction, maybe if A is half, is okay. It is a scaling, bracket, enlargement or reduction of center. Always you should know the center of the transformation of center B all over 1 minus A, and scale factor A. That is it. So that is a geometrical interpretation when A takes maybe the value 2 or half. So it is a scaling, or it's a homotheity. We can also talk about homotheity. It's a homotheity, yeah, of center B all over 1 minus A and scale factor A. Easy to retain. Now if I want to do a geometrical interpretation here first, let me show you. It's okay. If I have maybe this is the real, imaginary and real. Okay, if I have maybe, if the image maybe is point M, is okay. I want to apply a scaling to point M to have M prime. The first thing to do is first of all identify the center of the transformation from where I will start transforming my point M. That is the meaning of center of the transformation. If I see the center of the transformation is here, I will denote it maybe by gamma. If this is the center of the transformation, from this point, I will apply now what? An enlargement. So I'll apply an enlargement of point M to have M prime from the center. Are we together? It's from the center that I apply now the enlargement. Like if maybe the scale factor is 3 times M, is from here, that will apply 3 times M. So 1 time, 2 times, 3 times. I have my image M prime. That is the meaning of scaling, homotheity, enlargement. Okay. Now the next condition on A here will be leave this one. Now if it happens that A is a complex number excluding 0, when I'm putting like this, means there is a complex number. A is any complex number excluding 0. Yeah, if it happens that A is a complex number excluding 0, what do we do here? We calculate the magnitude of A. We calculate the modulus of A. So if A is a complex number, together, we calculate the magnitude of A. Now, let us see the condition on the magnitude of A. If the magnitude of A or the modulus of A equals to 1, so if the modulus of A equals to 1, we see that what? We see that T now here, we describe a rotation of center B all over 1 minus A and angle A. Are we understanding what I'm saying? So if A is a complex number, like what we were doing here, A was not a complex number, A was a set of real numbers. It was taking -1, it was taking 1, 2, and all those things. Now if it happens that A is a complex number and I calculate the modulus, it gives me 1. It means that here T now is a transformation that describes a rotation. So T is a rotation. T is a rotation of center B all over 1 minus A, always. Yeah, a rotation of center B all over 1 minus A. Now, when we're talking about rotation, we should have the center and the angle of rotation. Okay, and angle, center B and angle, argument of A. As easy as that. So this is the geometrical interpretation. So if I'm having a complex number Z prime equals maybe A plus IB Z, maybe plus I don't know, let's say C. Okay, you see that one. A plus IB is already a complex number. I'm already in this case. Now I can create the magnitude of A plus IB, give me 1. Therefore, I can give the geometrical interpretation of this transformation. T is a rotation of center B all over 1 minus A. Okay, so this is B all over 1 minus A. And the angle is what? Argument of A. Okay, let me show you it here. It's quite easy. It means that if I want to show it geometrically, so now for those that we wish to do concours, yeah, if you're doing further math, it means that you're willing to do engineering, and if you want to enter some of the prestigious school like Polytechnic, Yaoundé or Douala, you surely pass through concours and you surely do preparations. Yeah, so this similarity transformation will be well explained again for those that will do prepare concours at Confidence Corporation. Yeah, I will really well explain this thing again, showing how the transformation is really going on when you are having a plane. Yeah, now because Francophone really master it, so if you want to if you want to write a concours with Francophone, generally competition, yeah, you should also master it. And the only way for you to master it is to do prepare concours. So as I was saying, if I'm having my complex plane like this, real, imaginary, okay. Now, if I'm having my point M, which is the object, is okay. Now, let's just say our center is still here, gamma. Now, I want to apply a rotation to my point M in order to obtain the image M prime. So I'll first of all, for my center, always, because the transformation is from the center that we apply the transformation. For my center, I will rotate it by an angle of theta to have point what? M prime, where theta here is argument of A, and where the angle gamma here is simply what? B all over 1 minus A, as simple as that. So this is the geometrical interpretation. That is it. It means that when I apply it algebraically, it's the same as taking this thing like this. From the center, I take point M, I rotate it like this to have point M prime. So that is what we are doing geometrically. Okay, now let us go and see the last condition. Our last condition now is the modulus of A is different from 1. Yeah, if I calculate the modulus of A is different from 1, it means that what? It means that the modulus of A maybe can be 2, 3, 4, or it can be half, and all those things. It means that that is already scaling. There's a scale factor. It's okay. It's already, it means that the coefficient, the modulus there is already doing something to my Z. It means that the shape, the side will change. Exactly. It means for rotation, there was no change of the size. I will only rotating my point. It's okay. But now see here, since the magnitude is less than 1, is different from 1, it means that there will not be only a rotation, there will also be what? A scaling. It's okay. So anytime the magnitude of 1 now is different from 1, what is the geometrical interpretation? We will say that what? We will say that T here is a combination of a rotation and a scaling. Are we understanding? It will be a combination. So T is a combination of rotation and scaling of center. Now the center here will still be B all over 1 minus A, comma, of center B all over 1 minus A, comma, center this, comma, angle. Now angle is what? Argument of A, and at the end scale factor at the end scale factor of modulus of A. As simple as that. I think it is clearly explained. So if the magnitude of A or the modulus of A is different from 1, T now we describe a combination of rotation and scaling. A rotation and a homotity of center B all over 1 minus A, angle argument of A, and scale factor modulus of A. Now let me show you how I can draw it here rapidly. It means that if this is my imaginary, this is my real. Let's say my point M is T here. Is okay. Now if I say that this is the center of rotation, gamma, this is my center of rotation, it means that I will first of all apply what? I'll apply a rotation from my center. I'll apply a rotation of an angle theta. The transformation is not finished. I will not come and take M per minute. No. After applying a rotation of that angle theta, I will now apply a scaling. I will now enlarge, it depends if it's an enlargement, by a factor of magnitude of A. So this is my M prime. I will apply a scaling by a factor of magnitude of A. So you see what is M prime? Rotation plus, let's say rotation, like it's like a translation. A translation with the center gamma. So there's a brief record on similarity transformation. So if you master this, no question on similarity transformation will bother you. So now let us proceed with the sample question. So the sample question here is question 7. A transformation f on a complex plane is defined by z prime equals to negative I z plus 2i. The first question is find the image of the point z equals to 3 all over 2 plus I. Find the image of the point z equals to 3 all over 2 plus I. Okay. I think this is quite easy. It means that if I want to find the image of this point, I should take this point and put inside my transformation. I'll have the image, which is z prime. So let us with time. So I will substitute in z prime equals to negative I z plus 2i. When I will substitute, I will have z prime simply equals to negative I into 3 all over 2 plus I, then plus 2i. Are we together? So now here I will have a negative 3 all over 2. I times I is I square. I square is negative 1. With this one I have plus 1 plus 2i. So I will have negative 2 all over 3 plus 2, all this I plus 1. Now LCM here, I will have LCM is 3. I will have negative 2 plus 6. Negative 2 plus negative 2 plus 6 is 4 all over 3. I plus 1, so it is 1 plus 4 all over 3 I. So this is the image, as simple as that. Now if it happens that we were doing the image and it give us back this one, therefore that image, that point or that object is an invariant point or invariant object, is okay. And you should know that NB, anytime you are finding the invariant point of a transformation, that point should be the center of all the transformation, all the different transformation. I hope you understand it. So the invariant, should also know that the invariant point of a transformation is the center of the transformation, the center of the transformation. There's a small element that you should know, because in some question they will ask you find the invariant point, hence maybe hence describe what the transformation. From there, when you're describing the transformation, no need to calculate again. You take the invariant point as your center. Okay, so that is it. Now the next question Roman 2. Exactly as I was saying, Roman 2, determine the invariant point of f in the form a plus ib. If I have z, if f is a transformation, z equals to z prime equals to negative I z plus 2i, exactly. So the invariant point means invariant implies z should be equals to z prime image equals to the object. This implies z equals to negative I z plus 2i. Put together, I will items together. I'll have plus I z equals to 2i. I factorize. I'll have 1 plus I equals to 2i. So z equals to 2i all over 1 plus I. Now, I should not leave it like that. I should put my answer in the form I plus a plus ib. So I will do the conjugate. Here, the conjugate is 1 minus I. I multiply top and bottom by the conjugate to remove a complex number in the denominator. I'll have z equals to 2i times, I'll have 2i times, yeah. Then 2i times negative I, I'll have, is 2. I'll have plus 2. Yeah, taking that because I times I is negative. Yeah. Then divided by 1 plus 1. So I'll have 2 plus 2i all over 2. So that invariant is simply what? 1 plus I. So that is the invariant point under the transformation f. Okay, then the next question. So let us keep it here so that we should not forget. I think we will use it after. So the invariant point is z equals to 1 plus I, showing that it's already the center of the transformation f. Okay. Roman theory of the equation is show that f is a similarity transformation, stating its radius. You see, simply since you see it's very easy, since z prime is written in the form az plus b, where a is negative I and b is what? B is 2i. Therefore f is a similarity transformation of radius what? Magnitude of a, and magnitude of a is magnitude of negative I, which is what? 1. As easy as that. You are not calculating. When you know it, you state it, you have your mark. Roman 4, give the geometrical interpretation of the transformation f. As we can see, a here is a complex number, and the magnitude of a equals to 1. Therefore, f will be what? F is a rotation. So therefore, f is a rotation of center. Now the center is what? Of center 1 plus I, and what? F is a rotation of center that an angle of rotation. Now angle of rotation here, argument of 1 is what? Argument of negative I, you should know it's quite easy. Argument of negative I is alpha equals to tan inverse of negative 1 over 0. And we all know that one negative 1 over 0 is tan inverse of infinity, and tan inverse of 0 is pi over 2. Now you locate, pardon, we don't put negative, then, yeah, alpha we don't put negative. Now you locate the quadrant. Look at the imaginary part is negative, means that you're on the 4th quadrant. Therefore, theta is what? The argument is negative pi over 2. So f is a rotation of center. This an angle of rotation negative pi all over 2. You have your mark. As easy as that. F is a rotation of center 1 plus I, and angle of rotation negative pi all over 2. Yeah, and we all know that what you can also say, yeah, for a student that is really understanding what he's doing, negative pi over 2 is a clockwise rotation. Yeah, if you remember. So it means that f is a rotation of center 1 plus, is a clockwise rotation of pi of angle pi over 2 and center 1 plus I. Another student can write it like that. It's still I. So that is all about the equation. You see, if you really master the definition and the record that I gave, this thing cannot be more than you. And those questions are similar. Go now on any past complex number question talking about similarity transformation, they will be the same. Find the invariant point, describe the transformation, all those things. It's exactly the same thing. Find the image. So that is all. So that is all about the question. So students, stay to the end, because I would now like to solve another sample GCE question that we're talking about complex sequence and series. Yeah, it came in 2020, so I wonder we should do it so that no question on complex number will be more than you. Okay, now let us move to Next sample question here is saying that solve completely the complex equation. So I can leave you, I can even leave you to solve this one. Yeah, it's not difficult. Negative 27 I think this one is not difficult, right? If you want to solve completely this, I'll use exactly what I said. I should first of all represent negative 27I at polar form. To represent it, I'll first of all do its magnitude. The magnitude will be simply equals to square root of negative 27 all square, since the imaginary is only made up of the imaginary part, so it will be we cancel, it will be simply equals to 27. Now the argument of z will be simply equals to what? I'll first of all go and find alpha, which is tan inverse of imaginary part, negative 27 divided by real part, which is 0. Don't take the negative, okay? As you usually do, we don't take the negative. After taking only the positive part, the number, then we go and locate inside our quadrant where it is located. Now here we know that infinity times is pi over 2 put together, and since the imaginary part is negative, therefore the argument of z is simply equal to negative pi over 2. I hope that you know that tan inverse of infinity is 90 degrees. Okay, now if I have this, it means that my negative 27I in polar form is simply equal to what? Is simply equal to 27 exponential of negative by the exponential of I in bracket negative pi all over 2. So with that value, I can simply say that z cube is simply equals to 27 exponential of negative exponential of I in bracket negative pi all over 2. And using now the math theorem, it means that zk is simply equals to what? Cube root of 27 exponential of I in bracket negative pi all over 2 plus 2 pi k all divided by 3. I'm applying the math theorem as easy as that. Now another one, the cube root of 27 is 3 exponential of I into, multiply this one inside, pi all over I think 6 plus 2 pi k all over 3. Now z equals z to the power 3. We all know that what z k, we take the value 0, 1 and 2, so k of 0 is simply equals to what? It will be 3. If I pay by 0, e all over I negative pi over 6. It's okay. Then to put it algebraically is not difficult. Yeah, it will be 3 cos now cos of negative pi over cos of pi over 6 minus I sine pi over 6. I will all know that what pi over 6 is what? Pi over 6 is in degree, I think it's 30 degrees, so it will be 3 root 3 all over 2 minus I root, this half please, this half. Therefore the answer is 3 all over 2 root 3 minus I. That's it. Then you do same now with z1. It's okay. Z1 will be 3 exponential of, when I have 1 here, it means I will have a negative pi all over 6 plus 2 all over 3 pi. LCM 6. I have negative pi 3 plus 6 divided by 3, 2 plus 4 pi. Yeah. Then we make how many? 4 minus 3 is 3 pi all over 6, which is pi all over 2. That's it. So I will have here will give us 3I pi all over 2. I will know that pi all over 2 is what? Pi over 2. If I replace cos pi over 2 is 0, and sine pi over 2 is 1, so it will give us 3I. Then the last one now is z what? Z0. Now z2 will be 3 exponential of I. So I will have a negative pi all over 6 plus, when z takes the value 2, I will have 4 pi all over 3. Okay, then here the LCM is still 6, so So negative pi 2 plus 8 pi. Okay, then I'll have 7 pi all over 6. Okay, now so I'll have here 7 pi all over 6. Okay, so when you simplify, when you replace inside cos and sine, you simply come out with negative 3 all over 2 into root 3 plus I. So that is it. So making the solution, therefore the solution is 3i, comma 3 all over 2 into root 3 minus I, comma, and then negative 3 all over 2 into root 3 plus I. So that is the solution. Those are the 3 roots of the equation. Then the next question now is talking about the next question is on it's on simulated transformation B. Find the center and the scale factor of the transformation described by omega equals to 3z plus 2 minus I. Okay, we all know that I can even describe it. So the person that will complete this video would already know that what. Look at 3 is written in the form z z prime, because it's the image az plus b together. Now a is 3, showing that what it is a scaling. It's okay when a is 3 and it's a rail, therefore we are talking about a scaling of what? A scaling of center. So it means that the transformation T is a scaling. That means enlargement or reduction, but here will be enlargement. You can even say that A is an enlargement. Yeah, you can even say that it's an enlargement directly. So in bracket, it's a scaling bracket enlargement. It's an enlargement of of center. The center B all over 1 minus A, and a scale factor A. That is it. So now they are asking about the center. So I know that the center is simply equals to B. B is what? B is 2 minus I all over 1 minus A, which is 3. So making 2 minus I all over negative 2. So it will be negative 1 plus I all over 2. I think there is now, yeah. Negative 1 plus I over 2, there is the center. Then the scale factor that they are asking for. The scale factor is simply because you don't need to calculate here. Scale factor is the value of A, which is 3. So that is it. That is what they are asking for. Now let us move to the next question. Given that Z can be written as half into cos theta plus I sin theta. It's okay. It means that in polar form we Z half exponential of I theta. Same thing. And if we want to apply now the math theorem, I have Z to the n will be simply 1 over Z to the power n into cos n theta plus I sin n theta. Okay, that's from the math. So we are asked to show that the sum, that is Homer 1, the sum from r equals to 0 to infinity of 1 over 4 to the power r cos 2 r theta, yeah, is convergent. Now I think we put this sequence and series. Yeah, this sequence and series. So for a sequence to be convergent, there are 2 conditions. Exactly. They are asked to show that it is converging. It is a converging geometric progression. Okay. To show that it is a converging geometric progression, there are 2 conditions. For a sequence to be a converging geometric progression, it should first of all be a geometric progression. So for it to be a geometric progression, if you take the preceding term divided by the previous term, it should give you r, where r belongs to a real number. R is called what? The common ratio. We page it to already geometrical sequence and series. Now when it is a GP, now this to show that it's a GP, to show that it converges, you should prove that what the modulus the magnitude of r is less than 1. we are together, because we all know that what for a geometric progression, for us to have the preceding term, we should multiply by the common ratio. And if the common ratio is less than 1, example, I can take 2, it means that when I will multiply by half, you see that the denominator will still decrease. It means that the series is what? The series seem to converge. The series tend to converge somewhere. It means that it will finish somewhere. Whereas when the magnitude is greater than 1, maybe 2, when you multiply, you see that maybe when the first term is 1, you multiply by 2, you have 2, you multiply by 2, you have 4. You see that the sequence have the tendency to diverge, to go to infinity. So that is the condition for us to have a GP that is converging. Now, this is our series here. R equals to R theta. Now, for us to show that the series possess a common ratio, we should come up with like 2 terms or 3 terms. So, for saying, we all know that what the complex number, let's say exponential of I to R theta is simply equals to cos cos 2R theta plus I sine 2R theta. Are we together? Now, we also know that cos 2R theta here will be the real part. So, cos 2R theta is the real part of exponential of I to R theta. We should understand, it's very important. This is the imaginary part, this is the real part. It's okay? It means that this sum, the sum from I equals to 0 to infinity of 1 over 4R cos 2R theta is simply the same as the real sum of 1 over 4R exponential of I to R theta. Is that when I expand this, I will move over the real part. I'll come back to this. The real part of that will give me the first term will be 1. The second term will be 1 over 4 exponential of 2 of I to theta. The third term will give me 1 over 1 to 16 exponential of I for theta. Okay, so from there it means that when I will take exponential of I to theta all over 4 divided by 1, it will give me exponential of I to theta all over 4. So it means that this is the common ratio. Okay, magnitude of R now will be equals to magnitude of exponential of I to theta all over magnitude of 4. Now, magnitude of this is 1. I think we know it because it's the same as magnitude of cos 2 theta plus I sine 2 theta divided by 4. And the magnitude of this one, the modulus is like calculating cos squared 2 theta plus sine squared 2 theta. Okay, and square root of that. So this one is 1, square root of 1 is 1. So making it to be 1 over 4. Therefore, you conclude that it is a GP, it's a converging geometric progression because it's having what a common ratio which is 1/4, and that common ratio is less than 1. So that is the first part of the question. The next part of the question now we are asked to show also that Roman 2, the sum from I equals to 0 to infinity of 1 over 4R cos 2 theta can be written as 4 into 4 minus cos 2 theta divided by 17 minus 16 cos 2 theta. So we are asked to prove that. It means that we are asked to prove that the sum from R equals to 0 to here is equal to that. Now, you can notice something. When I'm summing from 0 to infinity, it's the same as doing the sum to infinity of a geometric progression. And the sum to infinity of the geometric progression is a formula bullet, and you know it. It's the first term all over 1 minus the common ratio. This, and we all know that what the magnitude of the common ratio is 1. It's only true when the magnitude of the common ratio is 1. Is less than 1, but okay. I think from here now you can apply. Means that the sum to infinity that we are looking for is the first term. The first term is 1 1 minus now the common ratio, which is exponential of I was of I 2 theta all over 4. If I remember, that was the value of the common ratio. Let us simplify. I will have 4 will go up. I will have 4 minus exponential of I to 2 theta. So now let us see how to simplify this. It means that the sum to infinity will be equal to 4 all over 4 minus, let us see, here is the same as cos 2 theta plus I sine 2 theta. Put together, yes. So for the proof to come out, it means that you can all see that you're not having I, so I should do the conjugate here. Let us arrange. I will have 4 minus cos 2 theta, then plus I sine 2 theta. So there's it. So I brought real together without forgetting that I'm taking the real part only. I'm taking only the real part. Yeah. Because since at the beginning I was taking the real part, this means the real part of the exponential of that is okay. So I'm taking the real part of this. When I finish to calculate, I will only take the real part. I will leave the imaginary part. We don't need that one. Okay. Now it means that from here now I should do the conjugate to remove the complex number in the denominator. I should do the conjugate. Doing the conjugate means I should multiply top and bottom by I should rationalize, but it means I should multiply top and bottom by the conjugate of the denominator. And the conjugate of the denominator here is simply 4 minus cos 2 theta, then minus I sine 2 theta. I do same down, 4 minus cos 2 theta minus I sine 2 theta. So there is it. So I will obtain, from here I will obtain, when I will multiply here, I will have 4 into 4 minus cos 2 theta minus 4I sine 2 theta divided by, all know that what I have, A plus IB, then A minus IB is simply equals to A squared plus B squared. So I think you know it already. So it means the real part square, which is 4 minus cos 2 theta all square, plus the imaginary part square, which is sine square 2 theta. Okay, now if I try now to simplify, here up I will have 4 into 4 minus cos 2 theta minus 4I sine 2 theta. Then here I will open here I will have 16 minus 8 cos 2 theta plus cos 2 theta square plus sine square 2 theta. This identity is what? Is 1. So I will have 4 into 4 minus cos 2 theta minus 4I sine 2 theta. Then 1 plus 1 is what? 1 plus 16, 17 minus 8 cos 2 theta. As easy as that. Now, you know that you can now see that it's not exactly the proof because it's still the imaginary part. As I was saying, I will take the real part of that. Taking the real part of that means I'm eliminating the imaginary part. So I will eliminate this part. That this is a fraction. You can still write it as sum to infinity equals to 4 into 4 minus cos 2 theta divided by 17 minus 8 cos 2 theta. Then then minus 4I sine 2 theta all over 17 minus 8 cos 2 theta. So taking the real part of this, I'm not taking this one, I'm taking only the real, means that the sum to infinity is simply equals to 4 into 4 minus cos 2 theta divided by 17 minus 8 cos to theta. Okay, so student, that is it. I think there should be a small error here. Here should be 8, not 16, because I'm coming out with 8. I think that there was a small error in the equation. Here should be 8. 17 minus 8 equals to theta. Okay, students, so that is all about the equation. So I think it really helped you. See you for another amazing